Welcome back to Nick's Algebraics. Today, I'm going to talk about how to factor quadratic expressions.
Woo!
Yes. As usual, I'll put the blank and filled out guided notes in the description so you guys can all follow along. So, I just want to start off by saying that factoring is an extremely important lesson that has a very special place in my heart because you will use factoring beyond your algebra class. Like you'll use it in pre-calc, you'll use it in calc 1, calc 2, calc 3, differential equations. It's all over the place. So, this is a very important must-know topic. Before I talk about factoring, I wanted to review the distributive property. This is a very important property. I even have a video on it that I made a couple years ago, so you guys can check that out. So the distributive property says that if I have A times B plus C, what I can do is I can distribute that A to both terms, and I'll get A times B plus A times C.
Are you not going to introduce us?
Oh my gosh, how can I forget? So with me today, I have the successful math club secretary and
Hey, gang.
Stickbuck.
Hello.
Wonderful. So that's the distributive property. Pretty simple, right? So for my first example, we're gonna use the distributive property to rewrite 6x times x minus 4. Let me just rewrite the problem. So 6x times x minus 4. Again, what I can do is I can distribute the 6x to each term. So what's 6x times x?
6x squared.
That's right. And then 6x times negative 4.
Negative 24x.
Yes, that's right. So minus 24x. So that's what you get when you use the distributive property. We're just rewriting 6x times x minus 4 as 6x squared minus 24x. All right. So let's talk about factors. So factors are the quantities that are multiplied together in a multiplication expression to get a product. So let me highlight that. So in this example right here, for example 1, the factors of 6x squared minus 24x are 6x and x minus 4. Because when you multiply the two, when you multiply 6x times x minus 4, you get the product. You get 6x squared minus 24x. And you've even seen this in elementary school, like the factors of 8 are 4 and 2, for example, because 4 times 2 is 8. So it's just the two things that you're multiplying to get the product. That's what the factors are. And factoring is rewriting an expression as a product of its factors. All right. So if you have a polynomial is basically like a sum of monomials and you're trying to factor it. So what you're doing is you're finding an equivalent expression that's a product.
I just want to say that I personally love polynomials. They're one of my favorite parts of math, and I just want to throw that in there.
I agree. Polynomials are number one in my heart as well. Next vocab word is greatest common factor, and it's abbreviated GCF. And the definition is pretty much in the phrase here. So it's an expression of the highest degree that divides each term of the polynomial. So highest degree just means like largest exponent. In any factoring problem, the first step is to look for the greatest common factor. We want to find the factor a bunch of terms have in common. So let's use that for example 2. So it says use the distributive property to factor each polynomial. So you're probably wondering, distributive property, what does that have to do with factoring? You guys were wondering that, right?
I was absolutely just wondering that. Yes, I was about to raise my hand and ask.
Great. So the distributive property, like I said earlier, you distribute the A and you get A times B plus A times C. But this also works in reverse. Like the distributive property also says that if you have AB plus AC, you can take out the A and write this as A times B plus C. So it works both ways. Like this is the distributive property, and this is also the distributive property. Like it's not called something else when you do it in the opposite direction. It's kind of like I don't want to make this too complicated, but it's kind of like log properties. Like when you have log of m to the power of n, that equals n times log of m, right? And if you do that in reverse, that's still called the power property. All right, so we're going to use the distributive property to factor these polynomials here. So we need to figure out what the greatest common factor is. Let's just look at the 6 and the 9. What's the greatest common factor of 6 and 9? Yes.
3.
Yes, that's right. So we're going to take out a 3. And what about for k squared and k to the power of 1?
Okay.
Yes, k. So you take out a 3k. That's the greatest common factor of these two terms. So when you take out a 3k, 6 divided by 3, that's 2. And k squared divided by k is k. And 9 divided by 3 is 3. And k divided by k is 1. So there you go. This is what you get.
I had that.
Oh, perfect. You get a gold star. You're a good noodle. So yeah, that's the distributive property. So we just factored out the GCF. You can factor any expression that has a GCF not equal to 1. So let's do the same thing for part B. So what's the greatest common factor of 7 and 35?
You want to take this one, stick bug?
Let's hear it.
Yes, that would be 7.
Yeah. And then for x cubed and x squared, I'll just say it. We can take out an x squared. So we took out a 7 from here, so you're just left with 1. And when you take out an x squared, you're just left with 1x. And then 35 divided by 7 is 5. And we took out the x squared, so this is what it is in factored form. And let's do one last one. This one's a little different. What can I take out from these two terms here? What do these two terms have in common?
X.
Just x?
Well, like, are we taking them out separately or like
No, just all at once.
stick bug, you take that one.
Like both of these terms have an x plus 3.
Oh, yeah, x plus 3.
Duh. I
So
thought you meant like everything.
yeah, it's all right. So both of these terms have an x plus 3. So I'm going to take out the x plus 3 like this. So x plus 3. So over here, we're just going to be left with the x squared. And over here, we'll just be left with the 5. And that's it. So yeah, that one was slightly more complicated. We're factoring out two terms now. We're factoring out a binomial. So both of them have x plus 3. So I just take out the x plus 3 from both terms and you'll be left with x squared plus 5. I purposely put this example because something like this is going to pop up later today.
Well, I'm really glad we covered it then.
Yes, now you know.
Now I know.
So example 3 is find each product. So we have a binomial times a binomial for parts A and B. You can use the distributive property to find this product here. Like you can do x times this x plus 2, and then you can do 3 times this x plus 2. So that's one way to do it. Or you can use the FOIL method.
I love FOIL. I was hoping you were going to say that.
Yes,
It's my favorite method.
FOIL is life. So
I'm going to get FOIL tattooed on me.
I'm going to have it tattooed on my leg, I think.
Where on your leg?
Probably on my ankle. So I can pull down my socks, my very long socks, and show people how much I love the FOIL method.
That's good. I was thinking like on my like ribs. So then anytime I'm in like a tank top or a swimsuit, it's like, oh my God, you love FOIL. And I'm like, oh my God, yeah.
Oh, okay. So the whole beach will know that you're so cool.
The beach will know. The whole river, the whole everywhere. They'll know.
Excellent. I like that.
Thank you.
So yeah, we're going to use the FOIL method. So the FOIL method is just like the shortcut version of the distributive property. So if you guys don't know, this is FOIL. So F stands for first. It's the first terms of the binomial. Why don't the math club secretary tell me what the O and the I and the L stands for?
So it's first and the F, and then outer because the L, and then inner because the I, and last. First, outer, inner, last.
Exactly. Let's use that. So the first is x times x, which is x squared. And then outer is x times the 2. So that's plus 2x. And then inner, we have 3x. And then last is like the second terms here. So 3 times 2, and that's 6.
I literally had that.
Nice. So is there anything we can combine here? Any like terms? Yes, stick bug.
You could combine 2x and 3x.
Yes, and what will you get?
5x.
Wonderful. All right, there you go. So that's the FOIL method. That's how you find the product of two binomials. So let's do one more example of this. So it's the same thing. First is x times x, so x squared. Outer is x times 6, so 6x. Inner is 5 times x, so that's just 5x. And last is 5 times 6, which is 30. And just like last time, you can combine these middle terms. So 6x plus 5x is just 11x. So there you go. That's how you find the product of two binomials.
We crushed.
Absolutely. But the thing is, today's lesson is about factoring. So everything in this page was just to like prepare you for factoring. This is like prerequisite review stuff. To factor, think of FOIL in reverse. Like we're going to have a polynomial like this, and we need to write it as the product of two binomials. That's the goal of factoring. So we have to FOIL in reverse. So I need to write this as x plus something times x plus something. So I need to figure out what those somethings are. So notice something interesting. 3 and 2, when you multiply them, you get that 6. And when you add them, you get that 5 right there. So it looks like there's some kind of pattern. And same thing over here. 5 times 6, you get that last term, you get 30. And 5 plus 6, you get that 11. So to factor a quadratic trinomial, here, I wrote it right here. To factor a quadratic trinomial of the form x squared plus bx plus c, you need to find two integers with a sum of b and a product of c. I want two numbers that when we multiply them, we get c, and when we add them, we get b. And just remember, this is only for 1x squared. Let's start factoring. Yeah, so let's do example 4. So factor each polynomial. So again, I want two numbers. I'm going to create like the x.
I forgot about the X. The X is the best thing ever, and I already know my numbers.
Good. So I'm going to create this x just to organize everything. So I need two numbers that multiply to get 20, to get c right here. And I want the same two numbers to add to 9. My successful secretary, what do you think those two numbers are?
I think that they are 5 and 4.
That's right.
Yes.
You get another gold star. So 5 times 4 is 20, and 5 plus 4 is 9. So in factored form, this is just x plus 5 times x plus 4. You see how we found those two numbers that multiply to get this number? We get c, and when we add them, we get b. So that's it. So the great thing about these problems is that you can easily check your work using the FOIL method. Like if you FOIL this, you're just going to get this original polynomial back. So if you FOIL it and you don't get this back, then you know you messed up. So that's the great thing. You can easily check your work. Let's do part B. What do we need to ask ourselves here? So this one, you might be thinking, okay, let's just find two numbers that multiply to 64, to multiply to C, and add to B, add to 28. But the problem is that this is not 1x squared. This is -2.
That's exactly what I was going to say.
Yeah, so this rule right here, it only works when you have 1x squared. So sadly, we can't do multiplies to C, adds to B anymore. But notice how all these terms have a common factor. Like what can I pull out from all these terms?
2, or would you want to pull out -2?
Yeah, I'm going to take out -2 because I want this to be a 1x squared. So
Exactly, so -2.
yeah, that's right. So I'm going to take out a -2. That's the greatest common factor. And you're going to be left with x squared here, 1x squared, which is what we want. And then 28 becomes -14. And then 64 becomes -32. So there we go. This polynomial here, now it's taking this form x squared plus bx plus c. So now we can use this right here. We can find two numbers that multiply to c and add to b. So we want two numbers that multiply to -32 and add to -14. So anyone have any idea what those two numbers would be? This one's slightly harder. So 32, forget about the negative. Let's just look at the factors of 32. Like there's 32 and 1. That's not going to get to 14. There's 8 and 4. That's not going to get you 14. And
It's 16 and 2.
there's 16 and 2. That will get you 14 somehow, negative 14 specifically. So
Negative 16 and 2.
yeah, so the 16 will be negative. So when we multiply these two, we get negative 32, and when we add them, we get negative 14. So in factored form, this polynomial here, this quadratic trinomial, is going to be x minus 16 times x plus 2. The negative 2 just kind of transfers over. And like I said earlier, like you can always just like distribute and you'll get the original polynomial back. That's how you can check your work.
How important is it to check your work?
It's very important because let's say you're taking an exam on factoring and you check your work for all the problems, then you know like you're guaranteed to get like an A if you checked your work correctly.
I used to do that in high school.
Yeah, same, exactly. And
110% and a gold star from my teacher, who I won't name.
yes, I would get a scratch and sniff sticker.
Yes, yes. Do you remember when we had the farm foods and one of them was like a potato?
A potato sticker?
Yeah, like, okay, actually, never mind. Fine, never mind. Fine, never mind. Forget it.
I don't know what kind of stickers you were getting, but I was getting like apple and like, but it's okay. Anyway, what I was saying is whenever you factor a polynomial, always look for a common factor first. Like for this example, we can take out that negative 2. So that should be like your first thought is there a common factor? All right, now let's go back to the FOIL method. Find each product. We have 2x plus 1 times x plus 3. So again, we're going to use the FOIL method here. So first is 2x times x. That's 2x squared. And then outer is 2x times 3, which is 6x. And then inner is 1 times x. I'll just write out the 1 just to make it very clear. And then last is 1 times 3, which is 3. And as usual, you can combine these middle terms and you'll get 2x squared plus 7x plus 3. All right. One more. 3x minus 2 times x plus 5. Same idea. It's first. So 3x times x is 3x squared. Outer is 3x times 5, which is 15x. Inner is negative 2 times x, so that becomes minus 2x. And last is negative 2 times 5, so that's minus 10. And when you combine these two terms in the middle, like 15 minus 2, you get 13. So this becomes 13x minus 10. So again, the goal is to factor quadratic expressions. So if I have a polynomial like this, I need to know how to get back to this, to a product of two binomials. Again, think of FOIL in reverse. So what I need to do is I need to split this 13 up into 15x and minus 2x if I'm going to do this in reverse. So how do I figure out the 15 and the negative 2? And same thing right here. How do I know to split this up into 6x and 1x? Why not like 5x plus 2x? So that's what we need to figure out. If I'm doing this in reverse, how am I going to split that middle term up to factor? So let's see if there's a pattern. Notice how 6 times 1, that's the same thing as 2 times 3. And 15 times negative 2, that's negative 30. And that's the same thing as 3 times negative 10. So what does it look like? The coefficients of those two terms are multiplying to. It looks like they're multiplying to a times c. A is like the number we're multiplying x squared by, and c is like the constant, the last term. So to split up that middle term, I want two numbers that add to get b, and those same two numbers have to multiply to get a times c. All right, so that's the next thing, is to factor a quadratic trinomial of the form ax squared plus bx plus c, and assuming there's no common factor, so you can't like take something out and make it 1x squared, then we need to rewrite the middle term bx as two terms, and the coefficients of these two terms will be two integers with a sum of b and a product of a times c. All right, so that's how you factor a quadratic trinomial, like in general. Let's do an example of this. So we're going to factor this polynomial. So again, I want two numbers that multiply to a times c and add to b. So what's a times c for this example? Remember, this is ax squared plus bx plus c. So what's a, what's c, and what's a times b?
C would be 24.
Yeah, a is 2, c is 12, so a times c is 24. So multiplies to a times c and adds to b, which is 11. So can you think of those two numbers?
Okay, let's talk it out. What is 6 plus 4? That's 10. That's not right.
Yeah.
10.
So 6 and 4 don't work. They multiply to 24, but they don't add to 11.
What about
Yes.
8 and 3?
Yes, 8 and 3. 8 times 3 is 24, and 8 plus 3 is 11. So what I'm going to do is I'm going to split this 11x up into 8x plus 3x. And what I'm going to do is I'm going to group the first two and the last two terms like this. So using the distributive property, I'm going to factor the first two and the last two terms separately. So I'm going to take out the GCF. So what's the GCF of these two terms, these first two terms?
2x.
Yeah, so 2x. And you're going to be left with x plus 4. And what can I factor out from the last two terms?
3.
Yeah, 3. And you're also going to be left with x plus 4. So we saw something like this earlier. What can I factor out from these two terms right here? What do they have in common?
X plus 4.
Yeah, we can take out an x plus 4, and you'll be left with x plus 4 times and then the 2x plus 3. So there you go. That's how you factor this polynomial. Notice how I couldn't just take out the 2. Sadly, I can't just make it 1x squared and just do multiplies to c and adds to b. So I had to do it this way. So this is called factoring by grouping. We're using the distributive property to factor polynomials with 4 or more terms. So that's called factoring by grouping because the first two and the last two terms are put into groups and then they're factored. And then again, you can, distribute and you'll get back to this polynomial. So let's do one more example of this. Again, notice how it's not 1x squared. A is not 1. And I can't take out a 4. Well, the greatest common factor here is just 1. So I need to find two numbers that multiply to a times c and add to b. So what's a times c? Yes, stick bug.
-12.
Yeah, because a is 4, c is -3. So a times c is -12. And then adds to b, b is just -4. So can anyone think of those two numbers?
Well, I was trying to look at it the way you taught us by taking away the negatives first.
Okay.
I was thinking 6 and 2.
Okay.
So I was thinking -6, +2.
Yeah, exactly. So a good, idea is to just don't worry about the negative, just look at the 6 and the 2, and then later figure out which one has to be negative. So the 6 has to be negative because we want these to add to -4. So -6 and +2. So I'm going to get this -4x. I'm going to split it up into -6x plus 2x. So 4x squared minus 6x plus 2x minus 3. All right. And it doesn't matter which way you do it. You can say 2x and then minus 6x. You'll get the same answer. It'll change the process a little, but you'll get the same answer. So again, I'm going to, group the first two and the last two terms. Again, this is called factoring by grouping. So what's the greatest common factor of the first two terms?
2x.
That's right. And you'll get 2x. And then when you take out 2x from the 6x, you're just left with 3. And what can I take out from the last two terms? Nothing really. The greatest common factor is 1. So I'm just going to emphasize that we can't do anything there. So I'm just going to put a 1 in the front and say there's 1 times 2x minus 3. But now if you look at these two terms, what's the greatest common factor? What can I pull out from those two terms here? Let's go with stick bug.
Okay. 2x minus 3.
Yes, 2x minus 3. So you're going to get 2x minus 3 times 2x plus 1 right here. And there you go. You can use this approach when a equals 1 because imagine right here for this problem, I asked myself what multiplies to a times c. Well, a is 1, so a times c, you're just going to get back to multiplies to c and adds to b. So this is like a special case where a equals 1, where you can just do multiplies to c and adds to b, and the two numbers you get are the two numbers that go after the x. So this is like a special case of this. This is like the general way of doing it, where a equals anything. All right, let's move on to something else. So when you're factoring, there are some special patterns that may be used to get directly to the answer without going through the entire factoring process. So when you have a difference of squares, so that's a squared minus b squared, that equals a plus b times a minus b. You can use what we did earlier and find two numbers that multiply to c and add to b, but this formula will get you straight to the answer. Like, let's just try that. Like, multiplies to c in this case is negative b squared, and adds to b. B is the coefficient of the term in the middle is 0. So multiplies to negative b squared, adds to 0. You're just going to get negative b and positive b. Negative b times b is negative b squared, and negative b plus b is 0. So that's where the a plus b and the a minus b come from. So this is a shortcut. You don't have to go through the entire factoring process. You can just use this formula here when you have a difference of squares. And a and b here could be numbers, they can be variables, or they can be like expressions. Maybe this a is like x plus 3 or something. And for cubic polynomials, there are two patterns. There's difference of cubes and there's sum of cubes. A sum or a difference of two cubes can be factored into a product of a binomial and a trinomial. And there's a mnemonic for this. These two formulas are harder to remember. So there's a mnemonic for...
I love mnemonics.
Yeah, mnemonics are great.
They're so amazing.
Yeah, so the mnemonic for the signs of the factorization is the word SOAP. So SOAP will help you remember what the patterns are with the signs, whether it's positive or negative. So the S stands for same sign. So notice how when you have a cubed plus b cubed, the first binomial here is a plus b. It has the same sign. And if you have a cubed minus b cubed, you start off with a minus b. Notice how these two have the same sign. And then the O stands for opposite sign. So it's a squared minus ab when you're factoring a cubed plus b cubed. So notice how these signs are opposite. And same thing right here. So same sign right here, and then over here, opposite sign. And then lastly, AP, the last two letters of SOAP means always positive. So this part is always going to be plus b squared, whether you're doing a difference of cubes or a sum of cubes. All right, so same sign. Notice how it's either both negative or both positive. And opposite sign, and then always positive here. These are both always positive. All right, so SOAP. Isn't that just dandy?
And it makes you feel like super clean.
There you go. Yeah. One important thing to remember is that for both the sum of cubes and the difference of cubes, this quadratic factor right here, the trinomial, is prime. Do you guys know what it means for a polynomial to be prime? It means that it cannot be factored any further. Yeah, so polynomials that cannot be factored using integer coefficients are called prime polynomials. The fancy word for it is irreducible over the integers, but you know, it's easier to just say prime. These trinomials right here, just leave them. You can't factor them anymore. Some people, they use this formula and they try to factor this even more, and you know, it's not going to work out. So let's do, oh, and I just included a table here with all the perfect squares and the perfect cubes. So like over here, this is 9, this is 9 squared, this is 9 cubed. So the first row is just the number, the second row is the square of that number, and the third row is the cube of that number, because these numbers pop up a lot and it's good to like recognize them. Let's do 7a, factor each polynomial. So we have x squared minus 4. So does this look like a difference of squares, difference of cubes, or a sum of cubes? Roly-poly, how about you answer?
It's a difference of squares.
Yeah, because you can write this as x squared minus 2 squared. This is my a squared minus b squared. So notice how a in this case is x and the b is just 2. And remember the formula, it's a plus b times a minus b. So this is going to be x plus 2 times x minus 2. And that's it. So very important formula. You could, like I said, it's 1x squared. So I could have just done multiplies to c. What's c in this case?
Is it 4? Negative 4?
Yeah, -4. And then adds to b, it's just 0x in the middle. So it adds to 0. So what multiplies to -4 adds to 0? It's -2 and +2. So x plus 2, x minus 2. So you could have done it that way too, using what we know earlier. But this is a better way of doing it because it's a nice like shortcut. What about this right here? What does this look like? Is it difference of squares, difference of cubes, sum of cubes? We got 49 and 81. We got x squared. So
Would it be a difference of squares again?
yeah, another difference of squares. Because we can write this as 7 squared minus 81 is just 9 squared. That's in the table right here. So you can write this as the square of the quantity 9x, because 9 times 9 is 81 and x times x is x squared. So this is my a squared minus b squared right here. So a is this 7 and the b is the 9x. Let me just write that here. A is 7, b is 9x. So remember the formula for a difference of squares is a plus b times a minus b. So this equals 7 plus 9x times 7 minus 9x. All right. What about part C? This one's interesting. Notice how we have x to the power of 4 now. It doesn't really look like any of the special cases here. It doesn't look like a difference of squares. There's no cubes. So it doesn't look like a difference or a sum of cubes. So any ideas on how we can factor x to the power of 4 minus 81?
I'm not too sure.
So even though it's a difference of fourth powers, because 81 is 3 to the power of 4, it can be treated as a difference of squares. You can think of this as x squared minus 9 squared. Now it's a little more clear that if you rewrite it, you can write it as a difference of squares. So this is a squared minus b squared. So the a in this case is x squared, and the b is this 9. So remember the formula is a plus b times a minus b. So a plus b is x squared plus 9, and a minus b is x squared minus 9. But do you notice something interesting about the second factor, the x squared minus 9? What is that? Which one of the special forms is it? Difference of squares, difference of cubes, or sum of cubes?
Difference of squares.
Yeah, the x squared minus 9 is itself a difference of squares and can also be factored. So because I can write it as x squared minus 3 squared. So that means in factor form, that would be x plus 3 times x minus 3. Isn't that cool?
Yes.
That is the coolest thing I've ever freaking seen.
Yes. So all these formulas, the difference of squares and the sum and the difference of cube formulas, can be applied to situations with higher order exponents. So you just have to use your exponent properties. I don't have an example of this on here, but if you wanted to factor, let's say x to the power of 6 plus y to the power of 6, you can use the sum of cubes formula, because you can write this as x squared to the power of 3 plus y squared to the power of 3. So it looks like you have a sum of cubes now. All right. So these formulas right here, it can be applied to situations with higher order exponents. You just have to do some clever algebra using your exponent properties. All right, let's take a look at part D. This one's pretty tricky. So we have a squared minus 2ab plus b squared minus 25, and we're trying to factor this. Do you guys have any idea what we should do? Yes, stick bug.
Could you potentially split it up into a squared minus 2ab and then b squared minus 25 and then factor those?
That's a good idea. You're thinking like factor by grouping, kind of like what we did over here, right? So,
Potentially.
I mean, let's just try it. Like over here, you can take out an a and you'll get a minus 2b and then b squared minus 25. But the problem is that you can't really do much at this point because these two don't have a common factor other than 1. So that's a good guess, but you won't get very far. So what you should be doing instead actually is group the first three terms.
Okay.
Yeah, and then you can factor this. So
That's so crazy. I didn't know you were allowed to do that.
yeah, it's legal. So this is 1a squared, so we can just use this rule right here. So we need two integers that multiply to c and add to b. So c in this case is the b squared, and the b is the negative 2b here. So we want two numbers that multiply to b squared and add to negative 2b.
What about B and B? Well, B and negative B and negative B.
Yes, negative b times negative b is positive b squared. And then when you add them, you get negative 2b. So in factored form, this thing right here is just a minus b times a minus b. And then there's that minus 25 at the end. And a minus b times a minus b, that's just a minus b squared. So what does this look like now?
Difference of squares.
Yes, difference of, I think I put a bit too many examples of difference of squares, but
I feel like I've said difference of squares every time.
yeah, I promise this is the last difference of squares. There's just so much you can do with difference of squares. It just pops up all over the place. So remember how earlier I said A and B, they can be numbers, they can be variables, they can be expressions. So in this case, the A is A minus B. And this 25, you can write it as 5 squared. So in factored form, remember A plus B times A minus B, it's this plus the 5, A minus B plus 5 times A minus B minus 5. So that's what it is in factored form. So it's a little weird because it's a product of two trinomials now. Does that part make sense? That's kind of a interesting step there. This is my A plus B, I'll use capital letters, times A minus B right here. But now the A is this A minus B and the B is the 5. So that's the tricky part about this problem. All right, let's do part E. We have x cubed plus 8. What does this look like?
Sum of cubes.
Yeah, sum of cubes, because 8 is just 2 cubed. You can see that in my table here. The cube of 2 is just 8. So this is a cubed plus b cubed. So that means a in this case is x, and the b is the 2. So we just have to use our sum of cubes formula. So remember, same sign, so it's plus initially. So a plus b, so that's x plus 2, times a squared, so that's x squared. And it's opposite sign. Remember, SOAP, the O is opposite, so now it's minus ab, so that's 2x. And then always positive, so plus b squared, which is 4. And we're done, because remember, you can try factoring, but you're gonna hit a roadblock. The quadratic factor, once you factor the sum or difference of cubes, is irreducible. It's a prime polynomial. It can't be factored any further. So you're done right here. All right, and here is the last example of today.
Oh my gosh.
Yep. So what does this look like?
Difference of cubes.
Yeah, difference of cubes, because 64, if you look at my table, it's just 4 cubed. And 125 is just 5 cubed. So you can write 64x cubed as the quantity 4x, all cubed. And you can write 125 as 5 cubed. So this is my a cubed minus b cubed. So a is 4x and b is 5. So let's go back to the formula for difference of cubes. Remember, same sign. So a minus b. So in this case, 4x minus 5. And then times a squared. The square of 4x, you have to square the 4 and the x. So it's 16x squared. And then remember, SOAP, it's same sign because it's minus. And then it's opposite sign. So this is going to be a plus. AB, so 4x times 5, that's 20x. And then always positive. So plus b squared, which is 5 squared, which is 25. And should we factor this trinomial here, this quadratic trinomial?
I want to say yes because it feels too large, but I'm thinking you can't. It'd be a very large number.
You cannot factor this. I mean, you can try, but you're not going to get anywhere because, like I said earlier, the quadratic factors are prime. They're prime polynomials. So that means they can't be factored any further. They're irreducible.
About prime. Logan Paul, forgive me.
So yeah, that's it for today. if you're watching this, it's very important to practice factoring a wide variety of polynomials so that you can quickly select the appropriate technique. So yeah, that's it. So don't forget to like, subscribe, and comment, and I'll see you guys in the next video. Why don't our special guests say bye to the audience as well?
Bye, audience. Thank you for
Bye,
having us,
audience.
Nick.
Thanks, Nick.
Professor
Don't
Nick.
forget to share with your friends and
Yes.
family. And
Copy link. Copy link.
Mhm.
Smash that bell.
Send it to your group chats. Post it on Facebook. Post it on Nextdoor.